Hello, this is DiffusionRL, efficient training of diffusion policies for robotic grasping using RL-adapted large-scale datasets. Diffusion models work well for image, video, and audio generation, but their use in robotics, especially in complex tasks such as dexterous manipulation, is still a challenge. The main problems we address are insufficient data, noisy datasets, and poor generalization. To overcome these challenges, we developed an end-to-end pipeline that enhances samples from DexGraspNet dataset using reinforcement learning, trains a lightweight diffusion policy to generate stable action trajectories for a 5-fingered robotic hand, and validates performance using a pose sampling algorithm based on the statistics of the original dataset. This is an RL-based dataset enhancement pipeline. First, we conduct a pre-selection stage of sample selection in the original IsaacSim environment, then train the RL agent on a static robot pose. In more detail, the initial grasping actions and object pose from the DexGraspNet dataset are fed to the MoniScale environment. And then the RL agent learns to predict additional grasping actions to ensure accurate and successful grasping. After training on a static robot pose, we removed examples on which the agent failed to improve performance and used the remaining examples to train the RL agent in a dynamically changing robot pose environment. The resulting examples of successful object grasping were used to collect a new dataset for the diffusion model. The TD3 algorithm was used to train the RL agent, and the actor and critic models consisted of lightweight architectures of 4 linear layers. The results of training the RL agents are presented here. As can be seen from the plots, with dynamically changing robot pose, the RL agent was able to improve samples from the dataset to a high success rate of 90 to 100%. After 3 phases of the pipeline, a high-precision dataset was obtained for training the diffusion model. The recorded trajectories were recalculated taking into account the preservation of the history of observations and actions. Here we present the architecture of a lightweight conditional U-network for the diffusion model. In order to evaluate the performance of the diffusion model during its training, it was necessary to test it on data not occurring in the dataset. Therefore, a pose sampling algorithm was developed based on statistics from the original dataset. To test the sampled poses, 2 baseline metrics were developed to estimate the maximum possible distances between the object and the centers of the grip parts, such as the middle phalanx of the middle finger and the palm. The minimum possible distances between the point clouds of these grip parts and the object were also estimated. For an oblong object such as a banana, the angles of directions to its edges relative to the normal to the palm were additionally considered. Finally, a diffusion model was trained on the collected dataset whose high success rate, about 80%, on randomly sampled object poses during training can be seen here. A demonstration of each of the pipeline steps can be seen on this slide. This slide summarizes the main contributions of the paper. Our approach can be used in a wide range of real-world robotic manipulation tasks. It enables training diffusion models on large, pre-built datasets, which are adapted to specific conditions by lightweight RL models, thereby eliminating the need for manual data collection. Thank you for your attention.